Okay, in that case, let's move on. I remember one of you asked me this question: can you actually replace the max pooling operations with a stride bigger than 1 by a convolution? Do you really need to do max pooling? And at that time, I answered, no, you don't need. And if you were not convinced then, you're going to be convinced now, because this is more systematic. You can actually replace your max pooling operations with convolutions with a stride bigger than 1. That's the big picture. You have a feature map, and it's produced by some layer of your CNN. For max pooling, you're going to choose the infinity norm for subsampling. But to be generic, it doesn't have to be the infinity norm. It could be any LP norm, which is basically you do a summation over a small neighborhood of your pixels or your pixel of interest. And then if it's the infinity norm, these summations are going to collapse and you're picking out the maximum. Otherwise, there is still a summation going on. And this G function is going to give you the neighborhood with different strides. So R is the stride, I is the pixel of the output, H is the actual window, which is in the neighborhood of -k/2 up until k/2. So that's going to give you your window in the x direction. This is the window in the y direction. And in terms of channels, things are going to happen channel-wise. So there is no summation or max pooling over your channels. This is only over your pixels. That's the pooling operation, a generalized formulation for it. For convolution, you still have these summations. You still have this G function. There is no LP norm anymore going on, but you are going to have some weights. And we know that our weights, or you can call them convolutional weights, kernel weights, you can call them filters, they're going to be 4-dimensional tensors. They're going to have a height, a width, a number of input channels, the number of output channels. And there's going to be a summation over your input channels, which is basically vector matrix multiplication. So that's the exact formula for a convolution. This sigma here is your ReLU activation. M is the number of output channels, or we can think of it as the number of filters. And then to be precise about feature-wise or depth-wise convolutions, we saw them when we were trying to make our neural networks more efficient. This is going to end up being diagonal, these matrices. Whenever U is equal to O, that's going to be a 1. Otherwise, it's going to be 0, which means that you don't actually need to keep them. Your weights or kernels could end up being, rather than a 4-dimensional object, it could end up being a 3-dimensional object when you're doing depth-wise. Because a lot of those zeros, you don't have to store them. In terms of performance, if you remove your max pooling and replace it with a convolution with the same stride, you're basically merging these two layers together, you're going to get the same performance or even slightly better. So what is the idea here? You can go all convolution. You don't need to use max pooling. And then next session, we are going to try to visualize this, the all convolutional neural network. And out of that exercise, some nice patterns are going to show up. So I think I'm going to stop here. And for those of you who want to leave, you can leave. For those of you who want to stay and ask questions, I'll be around.